Good. Should have been. Should have been easy. Because it was just like what we did in class for a dropped object. All right. So, numero uno. Part A, the speed is just 39 meters per second. Part B is 78 meters. Number 2 is 1.23 meters, that distance. How far is distance? 3A is 0.45 seconds. 3B is 4.4 meters per second. Number 4 is 15.3 meters per second. Number 5A is negative 78 meters per second. Part B is negative 310 meters. Number 6A is negative 20 meters per second. Part B is 20 meters. Number 7A is 275 meters. And B is 7.49 seconds. Any of those you want me to go over, Miriam? You got it. Okay. Both parts? The second part. Okay, so you should have listed for your givens the VI of 0, the A of negative 9.81 meter per second squared, and the VF of negative 73.5 meters per second. In part B, you're looking for the time. I've picked VF is VI plus AT to do that. So if I move that around for T, you get VF minus VI over A. So the VF is negative 73.5 meters per second. The VI is going to drop out, and your A is negative 9.81 meter per second squared. So the numerator gives you negative 73.5. The denominator is negative 9.81. You divide those two numbers, 3 sig figs gives you 7.49 seconds. Okay. You're welcome. Anything else? Yep, Nikolai?
6B.
6B. Okay, so these are the givens for number 6. The VI is 0 meters per second. The A is negative 9.81 meter per second squared, and the T is 2.0 seconds. You're looking for D. The equation that has VI, AT, and D is VIT plus half AT squared. The VIT is going to drop out. So I would be doing half of negative 9.81 meter per second squared times 2.0 seconds squared. You've got the square. That is the most common mistake with that equation is students forget the square on the T. So when you do the square with it, you get negative 20 meters. Now that's a displacement. How far is a distance? So you're going to drop the negative sign to give me the scalar answer, which is 20 meters. Okay? Anything else? Yes, Khalees. Yes, because it asked for displacement. Vector has to include the negative sign. Miriam.
I didn't get to see the answer for 3A.
Okay, so 3A, the final answer is 0.45 seconds. Yep.
For 3B.
Yep.
Why is there no
Because I'm just asking you for how fast, speed. Anything else? Okay, today's quiz is on your Chromebook. You can use this homework to help you, and for scrap paper, you will need your pencil, your reference table, and your calculator. The quiz should be posted now. Let's see if it did post. Yep, it's there. So go ahead and take that quiz now for Unit 4A. And while you're doing that, I will get the video link for yesterday and attach that to yesterday's post. Sorry, but that didn't happen. Where the heck is it? When you complete the quiz, you can put your Chromebook away. Just keep out your other physics materials because we're going to work on finishing up those practice questions for objects thrown vertically upward.
We can just use the homework.
Homework? Yep.
And then not notes, right?
Right. Okay. Just wait for you all set, Ryan?
Yeah.
Okay. All right, ladies and gentlemen, let's now turn to page 5 in your packet. And what we're going to do is finish up these practice questions from yesterday that we did not get through for an object that is thrown vertically upward. Your assignment for tomorrow, Monday, is pages 7 and 8. Okay, pages 7 and 8. You're going to do your check steps just on page 7, not on page 8. Okay, so let's head there. Let's make a note of that. So on page 7, you'll see this says this is the homework for unit 4B. So this is due Monday, which is November 3rd. You're going to do the check only on page 7, not on page 8. Okay, just on page 7, but you do need to do pages 7 and 8. Okay, if I just look back at the other assignments, the quarter exam review packet, remember, is due Thursday next week. That's on units 1, 2, and 3. And you will be getting your unit 3 test back today before you leave. Most of you are eligible for corrections on this test. Those corrections are due Friday next week. That we only have one other test grade this marking period. That's your quarter test. And the quarter test looks just like a regular unit test. One class period, same format. It's going to count just like a regular test, but it's cumulative, units 1, 2, and 3. What we're doing right now will not be on that quarter test. This way you have time to ask questions on the stuff that you're getting handed back from units 1, 2, and 3. Unit 4, we will test next week. You'll get it back, but I won't be able to get your corrections back into me before the end of the marking period. So there's no point. I'll count that as your first test grade on the second quarter. Yep. Next week, that goes on second quarter. Okay. That will be your first test grade of second quarter. Okay. Even though it's happening next week, I'm just going to push the grade to the second quarter grade book. All right. So let's then look at finishing up the problems on page 5 and 6. That is our task this period. And then next period, we're going to do a lab that's related to free fall. So what we listed yesterday in part A is we just didn't get the answer for part A. So let me give you a minute to work on calculating that answer. I am asking you for how high, which is a distance. So go ahead and work that out. And let's see what we get for how high it goes. How high does this ball go? Sarah? I think you may have forgotten the square in the numerator. Check your math on that. Because that's not how high it goes. It goes a lot higher than that. Who's got a different answer? Nikolai?
26.0 meters.
No, you're close, but close does not count. You got to have it exact. Double check. Janicia? There you go. It goes up 25.8 meters. So let's just review the sig figs on that and the rounding rule. Nikolai, is this what you saw on your calculator? 25.80275.229. Okay. So if I want 3 sig figs, I go 1, 2, 3 places. There I am at the 8. I look at the next digit to figure out whether the 8 is going to change, and it's not. So that's why it stays 25.8 meters. Okay. Now let's do our check on this because I don't think we checked. Did we check this one? We did. We checked it in number 1. So let's just write same check as number 1. Like we did with the problems yesterday for 4A, or 2 days ago for 4A. If we've already checked that version of the equation, I'm not going to check it again with you. We'll just write down which problem you would go back to look at the dimensional analysis for. Yep.
So I did on my calculator, I did 0 minus parentheses 22.5.
Squared,
Oh, square.
right? There's a square after the 22.5. Okay. And then you have to put parentheses around the denominator, like I have written here.
Okay, yeah.
Got it? Okay. Now let's go to part B. Ryder, can you tell me what the unknown is for part B, please? Yes. So what letter is that? T. All right. Like we were talking about the other day, we want to try to avoid using this answer for this. Because if you mess this up, you're going to mess up that. So we want to try to avoid doing that. So let's look at what we have. We have a VI, an A, a VF. You're looking for a T. Gavin, any idea what equation you'd like to select for that? That's what I would pick as well. So now you got to move it around to solve for T. And when you do the algebraic manipulation for T, you get VF minus VI over A. Zoom in a little bit more. You get VF minus VI over A. So let's go ahead and do our substitution with units. In this case, the VF we had was 0. So that can drop out. So we're going to have negative positive 22.5 meters per second divided by negative 9.81 meter per second squared. So now you're going to go to your calculator and you're going to solve that to get a time with units and sig figs. There will be no direction on this because time is always a scalar quantity. We can't go backwards in time, at least not yet. Haley, do you think you have it? That is correct. Now, I am not boxing that in because this is not the final answer to the question. This value was calculated from the launch up to the peak. In other words, this is the time going up. The question asks you how long it stays in the air. That's not the time going up, because what is that ball going to do once it goes up? It's going to come back down. You remember yesterday what we talked about you're going to need to do with this then? I'm asking you for the hang time. Emma, any idea? What do you have to do to get the hang time, the total time up and down? Add what? Yeah, you just double it. Exactly. That's exactly what you're going to do. So the total time that we're looking for, T hang, is actually twice 2.29 seconds. Because that is just the time up to the peak, the time up. So go ahead and double that, please. This value is the time going up because it used the ending velocity as the peak velocity. And I want the total time in the air. The ball doesn't just go up. It goes up and comes down. So that's why you have to double it. Okay. Blake, can you tell me what that gives you for the hang time, please? Yes. And that is our final answer to the question. Now, we do have to check this. I'm going to do that up here. We're going to check the equation we plugged into, which ended up being negative VI over A, because the VF dropped out. Shelley, can you tell me what units we have for T, please? Yep, so that's S. What units, Jackson, did I get for VI? That's right. We ignore the negative sign because that would be dealing with a number. And Khalees, what's our unit for A? That's right. Now, this is the case where we're dividing by a fraction. You remember we talked about you're not going to divide by a fraction to show things canceling. You're going to change it so it's multiplying by the reciprocal. Very good, Janicia. So let's go ahead and change that. This way we can show how things cancel out. Maxwell, can you tell me what you see that's going to cancel, please? Yeah? Anything else? That's right. This second's going to cancel on that square. So now I see that I have seconds on both sides, and that checks. Make sense, everybody? Okay. You want to make sure you can show me those steps to get there. You can't just give me this and then give me this. You got to show me how you get there. Show things crossing out. All right. Can we go on to number 3, please? All right. Elisa, can you please read off number 3 for us? Yeah, so 2.62 meters is about the height of the ceiling. So if you can imagine a kangaroo the feet going from here, and then their feet would be at the ceiling level. That's a pretty high jump if you think about it. Kangaroos are actually very large animals. I don't know if any of you have ever seen them in person or not, but they are. If you ever have the chance to go to Australia and see them in person, that'd be pretty cool. So what are we going to circle here, Chaudhry, as a given? What can I circle?
2.62 as distance.
So we're going to circle 2.62 meters. Devin, what should I check off that or underline? Takeoff speed. All right. So let's go ahead and now start listing givens. Nikolai, a given, please.
D equals 2.62 meters.
Yep, that's right. Alex, something else?
VI equals 0.
No. We're looking for takeoff speed. So that's actually your unknown. I'll list that here. I'm looking for the VI. Jacob, something else I can list. Where's the kangaroo?
R.
Yeah.
So the acceleration is negative 9.81 meters per second.
Good. Now, when we get to this height, that's at the highest point. Ryan, what do we know about things when they get to the highest point? What does everything do at the highest point? They stop. That's where it's ending for this question. So what else do I know? VF is 0 meters per second. Okay, let's see if we can locate an equation that has a D and a VF and a VI. This is on page 6. Gianna, do you think you have that equation? That's the one I would use. Now we have to move this around for VI, which means we're going to get an equation that looks like VF squared minus 2AD, and then take the square root. So now I'm going to go ahead and do my substitution with units. VF squared is going to cancel out because the VF is 0. So I'm just going to do negative 2 times negative 9.81 meter per second squared times 2.62 meters. And now we're going to solve that for VI. I'm looking for speed, so I don't have to worry about a sign on this at all. Vincent, do you think you have an answer for me?
7.17 meters a second.
Meters per second. Very good. Now let's do our check. The equation we're going to check is the one we plugged into, and that VF canceled out. So it's the square root of 2AD, or negative 2AD. What units do I have, Sydney, for VI? Okay. I'm sorry? The VI? No, it's not. We took a square root, so the square goes away. So it's just meters per second. Now we're going to go to the right side, keep the radical. The negative 2 is going to drop out because it doesn't have a unit attached to it. Miriam, what is the unit for A? Good. Kiara, what's my unit for D? All right, so order of operations says we do what's underneath the radical first. So when I multiply that together, Janicia, what do I get under the radical? That is correct. And Ryder, when I take the square root of that, what happens? That is correct, and that checks. Okay? Are we good with 3? All right, let's move on to question 4. Gavin, can you read number 4 for us, please?
Michael Jordan was vertical movement of 1.29 meters, and what is A is takeoff speed and B is takedown, total time due upwards, and then return back to the top.
All right. So, Haley, what can I circle in this question? That is correct. What am I going to underline, Emma, in part A? That is correct. And Blake, what am I going to underline in part B? Hang time. All right. Now, it's a group question, so we only list the givens once for the whole problem. Shelley, how about a given for this question? Correct. Jackson, can you give me another given, please? Correct. And Khalees, how about another given? Is? That's right. Because when we get to this, we are at the peak. All right. What are we looking for, Maxwell, in part A? The VI. All right. Lisa, can you tell me what equation I should use in part A? Yeah, just like the last question. So when I move this around for VI, I get that VI is equal to the square root of VF squared minus 2AD. And since the VF, which is at the peak, is 0, that is going to drop out. So we can do our substitution with units like we did in the kangaroo question. That VI is the square root of -2 times -9.81 meter per second squared times 1.29 meters. Let's go ahead and solve that for Michael Jordan's takeoff speed if he is going to reach that height. Chaudhry, can you tell me what you got?
5.03.
And the units on that, please?
Meters per second.
Correct. Now, I'm not going to check it because this is the same check as number 3. So we don't need to repeat it. Let's go to part B. Devin, can you tell me what we are looking for in part B? So what letter? T. All right. We need an equation that we can use to help us get T. In this case, I'm not so sure that we have one that involves a D, an A, a VF, and a T. Do you see anything that has a D, an A, a VF, and a T? You do? What equation has a D, an A, a VF, and a T?
No, but
Okay, so because we don't have one, you can use your answer. You have to use your answer from part A to help you. There's no other way. Okay? You can use the VI in part A to also help you get the T. Nikolai, you have a question or an equation?
Yeah. D equals VI, T equals 1/2 AT squared.
Oh, this is the hard one. You can do this one, but because VI is not 0, you will have a quadratic equation to solve. I don't want you to do that way. Okay, so we're not going to use that one. There is another one that will make it so we don't need a quadratic equation. Alex, do you have an idea?
Is it VF equals VI plus H?
That's the one I would use. So if I move that around for t, I'd get VF minus VI over A. Now in this question, the VF is 0, so that's going to drop out. We're going to go ahead and plug in negative of the answer from part A, 5.03 meters per second, divided by negative 9.81 meter per second squared. So let's go ahead and solve that for a time. Jacob, any idea what that gives you?
I got 0.513 seconds.
Yes. Now, this is not the final answer to the question because we had a VF of 0. Where do we have a VF of 0? Where? At the top. So that is the time from the ground to the top. That means that's just the time going up. Do I want the time going up? Is that what I asked you for in the question? What time did I want? Hang time. Do you remember what you have to do to get the hang time? Double it, right? So let's go ahead and double that. And Ryan, we're going to keep 3 sig figs. So what does that give us? .03 seconds. That is our final answer. Now, did we check this version of the equation before? Can you look back at the previous questions? Did we check that? I think we did, didn't we? Where did we do that? To which part? B? Okay. So we're just going to say same check as number 2B. So that way you can practice that. Okay. Last one, number 5. All right, Gianna, go ahead and read number 5 for us, please.
Determine the height to which the ball rises before it reaches a peak.
Okay. Vincent, something I can circle.
Straight up.
I'm sorry?
Straight up.
No. That's not going to give me a given piece of information. Sydney, something I can circle in the question that I know. Yep, so I'll circle 6.25 seconds. Miriam, what am I going to underline? Height. Underline the word height. Now, there is a hint given to you that the time to rise to the peak is half the total time. We should know that anyway, right? Based upon our notes from yesterday and the previous questions. They're giving you that hint because when I list my givens, this hang time isn't really going to help me out in solving the question. Instead, we're going to think about the time up. How do we get the time up then? Ryder? Divided by 2. So it's half of 6.25 seconds. So Kira, what does that mean with 3 sig figs? The time up is? 3.13 seconds. Okay. Let's just see if we can finish off the givens on this. What else do we know about it as it goes up? Janicia, anything? Yep. That's at the peak. And Ryder, there's something else we know. Okay. Let's take our break, then we'll finish this up, and then we'll work on a lab.
Do we get to draw one of these like panels?
No, that's AP. If you come back next year, you get to decorate a ceiling tile at the end of the year. Every year, it's one of their projects. It's a research project, and then they get a ceiling tile to decorate that shows the theme of what they decorate. We're trying to create a timeline of physics concepts in the ceiling. And so you'll see that they indicate the year of the discovery or the scientist. They explain it a little bit pictorially what the discovery was, and then they sign their names on it with their year of graduation.
And the best one gets on
Now, there's multiple for each year. Yeah. So we've been doing this since 2021. So there are some tiles here from 2021, 2022, 2023, 2024, 2025. This year's class is the class of 2026. So when they break up into groups, they'll get a tile to decorate that shows their theme. Yep. And then it will stay up there till hopefully forever. I don't think it's going to be forever though, because when the ceilings upstairs, when they clean the floors upstairs, they pour water on the floors and the water leaks through. So like a couple of the tiles over there have gotten water damage, but it's not completely. There's a tile over there with some water damage. Try to keep them here as long as we can. This is not on the list to be renovated. Yep. Yeah. This room was renovated 15 years ago. It was not a renovation. It was, let's give you some electrical drops in the ceiling and let's buy you some new desks for the kids to sit. I was like, that's not a renovation. But that's what we got.
So you just stick with the projector.
They gave us a projector in the ceiling. So I wasn't using an overhead projector anymore. Have you seen those old overhead projectors?
Yeah.
Do you have those from elementary school probably? I still have mine in the back room because we do use it for some physics labs.
Is the chemistry also in
Nothing down here is slated to be renovated.
so not
No.
Are they gonna ever renovate the lunchroom?
It's not in this capital project. Maybe the next one. I don't know. Honestly, my opinion is we need to just start over,
what do you mean start?
build a new building from scratch
That was too expensive.
instead of fixing. But anyway, let's finish up number 5, okay? Now, based on what we had as givens, if I want you to find the height, what is it that is our unknown letter? Where did I leave off with that acceleration? Who gave me that value? Ryder, you did? Okay, so Gavin, what is it that we're looking for? D. Take a look at your reference table for a minute. Do we have an equation that's going to work? We do not. So what we have to do is come up with another way to do this. And it's actually fairly easy to think about it. What we did here is we looked at it going up. Instead of looking at the ball going up, let's look at it coming down. Because isn't the distance up the same as the distance down? Okay, so this is for what we did here is for the upward path. Let's change it and write the givens for the downward path instead. If we do that, what are we going to have? Not a time up, but a time down. Do we know that value? Should be the same thing, right? 3.13 seconds. It's not the VF that would be 0. It would be the VI, which is again at the peak, which would be 0 meters per second. And the acceleration, is that going to be any different because we're coming down instead of going up? Is the acceleration any different because it's coming down instead of going up? What determines that acceleration? The planet. Are we on a different planet? No. So it's still negative 9.81 meter per second squared. Now that we have these three as our given and we're looking for D, can we do it? Okay. Can we find an equation, Haley, that would make that work? That's right. I want to solve it for D, but remember the VI is 0, so this is going to drop out, so I can ignore that part. So I'm just going to do half of negative 9.81 meter per second squared times 3.13 seconds squared. Now, when I solve it, because acceleration is a vector with a direction, I'm going to actually end up with the displacement coming down. So let's go ahead and figure out what the displacement downwards is, and then we'll get the height. Emma, do you think you know what it is? I'm sorry? Don't forget your square. I think you forgot your square at the end. Good. Now that's the displacement. I wanted the height, which is a scalar. So Blake, what does that mean the height is? That's right. Now let's do our check because I don't think we checked this today. The equation we're going to check is D is 1/2 AT squared because the VIT dropped out. What units, Shelley, did I have for D? Good. The half does not have a unit, so we ignore it. Jackson, what is our unit for A? Good. And Khalees, our unit for T is? Good, which we'll get squared. Maxwell, can you tell me what happens? That's correct. So let's show that, leaving me with meters on both sides, which checks. So the moral of this is that if you end up working on a question here, where you end up saying, I don't have an equation that works for the upward path, just switch it to the downward path, and then you can solve it. Okay? Questions on that? Great. Let's put your packet away. Keep out your reference table and your calculator. I would like you now to take out your Chromebook because the lab is a virtual lab. This is the last lab that is going to count on the first quarter grade. We're going to get this done before we leave today. If you could all open up lab number 8, free fall. I'm going to work it through with you so that way we can get it done in a fairly good time. It's the one right plugged in. Yes, that's it. You got it. All right. So once you have it, this is what the lab is going to look like. It's a Google Sheet. No surprise. Our virtual labs are either Google Docs or Google Sheets. And I'm going to make mine a little bit bigger. Do this. You don't have to open up the video link because we're going to do it together. Okay. What we're going to do in this lab is try to experimentally determine the free fall acceleration of gravity here on Earth, G. And we're going to do that with some video analysis tools, which we have not done before. We're going to collect data from a video, a slow motion video. In fact, somebody took a video of something that was dropping. And what we're going to do, the video is linked in YouTube. You don't have to open it up. I'll open it and we'll watch it together. We're going to collect the data together because it is hard to read the video. So I'm going to help you with that. We're going to change the video settings in to 0.25. We'll see that at the bottom of the screen, time is going to flash at 0.1 second time intervals, which is going to allow us to freeze the video and then make position measurements. What we will do is for each of these 0.1 second time intervals is record the position of the freely falling object. We'll record it from the bottom of the object each time. We're going to read where the bottom of the object is and record it. And those measurements are going to go in the data collection tab. So let's all click on the data collection tab. This is where we're going to put all our data here in this first data table for positions. We're going to do this together. Let me switch over to the video. This is the video that's linked. I'm going to make this full screen. And let's just watch it in real time first. Seconds. You see those times flashing at the bottom of the screen? No way we can do that in that amount of time. All right. So what we're going to do is I'm going to adjust the playback speed, which is in the settings. Playback speed, we said to do it at 0.25, so slow motion. And we can actually step through this video. If I go ahead and play it, I can pause it. And I can go back. I think it's the arrow key, the left arrow. There it is. My left and right arrow keys allow me to move through like frame by frame. So that's what I'm going to do to help you do it. Now, I know it's really hard to see. Right? Really hard to see. Can you see that over here on the left, there are numbers written? Can you see that? That's where I'm going to help you out because mine is bigger than yours. But can you see that the bottom of the object is placed on a line that's right here? That's the 0 meter line. All right. So that's going to make things a little bit easier, at least for 0 seconds. So let's go back into our Google Sheet. And the position at time 0 seconds is 0. So just type 0 in there, hit enter. It's going to give it to us out to the hundredths place. We're going to use that for something else. All right. Let's go back to the video. And what I'm going to do is now right arrow over until I get to 0.1 seconds on the screen. You see it starting to fall? There it is. Now, this is where things get a little tricky. This is 0 meters, and this here is 0.1 meters. He has a little line that's halfway between 0 and 0.1. We're not quite there yet. We're a little bit above that line that's halfway between here and here. So I'm going to say it's at about, it's not even halfway. It's like at about 0.13. I'm sorry, about 0.03, because 0.13 would be beyond this. So our first position now at 0.1, right here, we're going to type 0.03. It's about 0.3 of the way between 0 and 0.1. Is everybody with me? Okay, let's go to the next one at 0.2 seconds. Back to this, share it. I will right arrow until we get to 0.2 seconds. There it is. Looking at the bottom, look at where it is. It's right on this line. If this was 0.1, what do you think that is? 0.2. So we're going to put that it's right at 0.2. All right with me? Okay, let's go to 0.3 seconds. Fortunately, we don't have too many of these that we have to do. There's 0.3. Okay, so this was 0.2. This line here is 0.3. There was a line here at 0.4. There's a line here at 0.5. I don't see the middle line. So guess where that means I'm at? Halfway between 0.4 and 0.5, which would be halfway between 0.4 and 0.5 is 0.45. All right, so let's go ahead and put that in, 0.45. Okay, I'm going to go back to the video, and now I got to get to 0.4 seconds. Oh, I hit the wrong arrow. There's 0.4. Okay, so let me try to help you out. This is 0.5. This is 0.6. This number here is 0.7. This one's 0.8. There is the line. Can you see my cursor at 0.8? Okay, we are not at 0.8 yet. And I don't see the line at 0.75, the halfway mark. I'm almost at 0.8, but not quite. I think I'm at like 0.78, something like that. Okay, so let's go back and type in 0.78. Now I'm going to go to 0.5 seconds in the video. There it is, 0.5. Okay, this is a meter. This is 1.1. This is 1.2. This is 1.3. I don't see the halfway mark, so I'm just a little bit beyond halfway between 1.2 and 1.3. Just a little bit. So maybe 1.26 or 1.27. I think I'm going to do 1.27. I think that's a better response. Now I'm going to go to 0.6 seconds. There's 0.6. All right, I got to do a little reading here. 1.3, 1.4, 1.5, 1.6, 1.7. This is 1.8. There's a little mark here at 1.85. So we are not there yet. Hold on a second. 1, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 8. Yeah, so we're not yet at 1.85. Maybe we're like at 1.73, almost halfway between 1.7 and 1.75. All right, the last one I have to get is at 0.7 seconds. Okay, there's 0.7 seconds, and this is going to be a little tricky because the line for the video is there. So let's see if I can help us out. This is clearly 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9. Right here is 2 meters, 2.0. 2.1, 2.2, 2.3. We are not yet at the line at 2.4. Actually, I think we're just beyond it. Here's 2.45, this little mark here. So I think we're halfway between 2.4 and 2.45. So I'd say like 2.43 as our last position. Okay. I don't need that video anymore. So I'm going to close it out just so I don't. I don't need the video, so I'm going to get rid of it. Okay. So now what I'm going to do, and you need to do this as well, is make a position time graph for that data. You remember how to do this? So let's select all that data, starting with time and position. You do need the column headings. Select the data, go to Insert, Chart. It says Scatter Chart. I'm going to make my screen a little bit smaller now so I can see everything here a little bit better. I do want a scatter chart, although yeah, that's fine. Let's go to customize it because I don't think anything is labeled on the graph. So to customize it, yeah, I got to edit things. Chart and axis titles. What should the title of this graph be? That's right. Position. That's under chart and axis titles. Position versus time. We need to change the horizontal axis title. I don't know why it gives me all of this. What's the horizontal axis title? Time in seconds. What should the vertical axis title be? Position in meters. Okay, I'm going to collapse that. I'm going to go to series. So I can add my trend line. What type of trend line do you think we should get? No, we're only in the first quadrant. So when we're only in the first quadrant, what can we pick? Remember? Does start with a P, but it's not polynomial. Power series. Good, Haley. It's power series. Check the power series one. There we go. I can now add my equation to that graph. So the label, say, use equation. That graph is now done, and I can click and drag it down on my graph to that location, which goes with question 2. Okay, everybody with me? Okay, I have to make mine a little bit smaller because it's, should look something like that. Okay, now in step 3, you'll see that there is a link. I want you to go ahead and click on that link. Open that up, and you're going to see that you get this website, which has a tangent line calculator. Let me explain what this is. What we're going to try to do now, what we learned in Unit 3, is that we can find instantaneous velocities from a parabolic shaped graph by drawing tangent lines at time points and finding their slopes. I'm not going to have you do that here. Somebody out on the internet went and did a tangent line slope calculator for us. So if I type in, and you can do this too, you see here, it asks you for an equation for the graph. We can get the equation from our graph. Oops. Our equation from our graph right here. Did you get 5.8x caret 2.21? We all should have that because we all had the same data as long as you typed it in correctly. We're going to take that equation and we're going to replace it in this box here. So what was it? It was 5.8 times x, so we'll just put x, caret 2.21. See it right there? 5.8 caret 2.21. Now, don't hit calculate yet. You see over here, it asks you, it says at x equals, and then there's a number. That's where we're going to put in the time values. So go back to your Google Sheet for a minute. And when you look at your Google Sheet, you'll see that I've given you in step 4 the time values. Those are the times that we want to plug in, and then that calculator will give us the velocity at each of those times. It will give us the slopes of those tangent lines. So the first time we're going to plug in is 0. So on our tangent line calculator, change that x to x equals 0, and then hit calculate. You'll see that it's doing the sum calculation to give you the slope of that tangent line at x equals 0. And do you see where it says result, and then it puts a 0 here? Result 0, that's the answer for the slope of the tangent line, which is our velocity. So we're going to take that answer, which is 0. We're going to go back to our Google Sheet, and we're going to type in 0 for the initial velocity. Doesn't that make sense? Didn't it start from rest? Okay, now we're going to do the same thing, but we're going to change the time to 0.1. So go back to your tangent line calculator, this screen, change that x value to 0.1. Hit calculate. It's going to do the calculation. It's going to come down, and it gives you a result, 0.790351. Is that what you're getting? So we're going to take that answer, 0.790351, and we're going to plug it into our Google Sheet at 0.1, 0.790351. It's going to round it. That's fine. Now we're going to do the same thing at 0.2 seconds, and so on and so forth. Can you do that yourself? Okay, let me give you a couple minutes to get all of those all the way to 0.7 seconds. But I'm not going to walk you through it. I'll let you do it. Go to 0.3. Answer. Copy it. Paste the value. Now go to 0.4. Get the result. Paste it. 0.5. Copy it. Paste it. 0.6. And one more at 0.7. Once you have them all, then you can close out that tangent line calculator. Now, once you have that, are we still getting data? Anyone still getting velocities? These are all rounded. What you're going to then do is make your velocity time graph for step 5. So we're going to click on time, right arrow over to velocity, select your numbers. We're going to go to the insert menu, insert a chart. Should be a scatter graph. Then I'm going to customize it with my chart and axis titles. I'm going to start with the chart title. This is a velocity versus time graph. Then I'm going to add my horizontal axis, which should be time in seconds. Then I'm going to add my vertical axis title, which should be velocity in meters per second. Now, if I look at that, I think I can predict what type of trend line I'm going to need. What does that look like to you? Line or a curve? Yeah, that looks like a line to me. So, and that's what we should expect. So let's go down to the series option, select trend line. There's a line. That looks really good. Hits almost all the points. Add your equation. And you can now close your chart editor. That graph is done. Click and drag it down into the yellow space for question 5. Okay. Now it asks us to go on to the analysis tab. Can I do that with you? We're going to answer these questions together. So if you're paying attention and you got the same exact data I have here, same equation, this will be easy. Let's go to the analysis tab. Number 1, for a dropped object in free fall, what is the shape of the position time graph? Well, let's look. What shape was our position time graph here? What's that shape? What is it, Ryder? It's a parabola. All right, so we're going to click in that red line, not change the color, just type parabola. Parabola is how you pronounce, not how you pronounce it, but that's how it spelled out phonetically. That's what that would be. Enter. Question 2. For a dropped object in free fall, what is the shape of the velocity time graph? Well, let's go back and look at our velocity time graph. What shape is that graph? Good, diagonal line. So let's answer that for question 2 in the red line. Diagonal line. Enter. Number 3. Question 3. What is the slope of an object's velocity versus time graph equal to? Miriam? That is correct. So let's type acceleration in that red line. Enter. Number 4. Based on this experiment's velocity versus time graph, what was the acceleration for a dropped object in free fall near the surface of Earth? So where am I going to get that? We basically told you in question 3 where to get it from. If I want the acceleration for this experiment, what do I have to do? Blake? Yeah, let's go back, look at our velocity time graph. What is the slope of this graph? You get it from the equation. Where's the slope in that equation? Please? It's the 12.1. So let's go and add that here. So on this red line here, I already have the units at the end. I'm just going to type 12.1 in there. The acceleration we got was 12.1. You have to tell me what you got. If you got a different number, then you got to put in what your number is based on your graph. Now, let's go to the next question. Number 5. What's the accepted value for the acceleration of a dropped object in free fall near the surface of Earth? Cindy? Yeah, the 9.81. That's its magnitude. So 9.81 is what we're going to put in there. Nope, because that's giving a direction. We're just looking for the magnitude. Now, number 6 wants us to do our percent error. I even gave you the formula right there. You're just filling in the red lines and the substitution with units and the final answer. So let's do that. What's the experimental value from question 4? $12.1. What is the accepted value that we're going to put on that red line, the AV? Lisa? 9.81. Good. We're looking for the percent error. I did that step. I gave you the equation. So now we have to type that substitution with units. So we're going to show the absolute value, then the left parenthesis. The accepted value is 9.81 with units, meter per second caret 2. That's meter per second squared. Minus the experimental value, which was 12.1 m over s caret 2. Then I have to close the parenthesis. Then I have to put my absolute value symbol divided by the accepted value, which is 9.81 m over s squared times 100%. Now, Google Sheets is not going to calculate it for you. You're going to use your calculator to do it. So let me give you a couple minutes to calculate that out, please. I think that's as big as I can go, Chaudhry. It's not letting me adjust it. Let's see if I can. There it is. You're welcome.
For the absolute value.
Yeah.
Put like a line.
Yep, vertical line. On my keyboard, it's above the slash that's tilted left on the right side of the keyboard above my enter key. I'm not sure where yours is because I have a laptop, not a Chromebook. You got it? Okay. We're going to go 3 sig figs. Give everybody a minute to get your answer for the percent error. If you have my numbers, you're going to get the same thing that I get. Anyone have it? What'd you get for that percent error? Janicia? That's it. That's with my numbers. That's what you should get, 23.3%. Now make sure you hit enter after you've typed that in, and then you can submit it. That's the lab. If you're not getting that, or you had different numbers that you got from your calculations, obviously you're going to get a different answer. Okay? Any questions? All right, that is the lab. Make sure you turn it in Google Classroom once it is all done. And you now have the rest of the time today to work on the assignments that are up on the screen. That is pages 7 and 8 in your Unit 4 packet, your quarter exam review packet, and I'm going to hand back your test. You can start working on test corrections as well if you want.